All right. In this lecture, I'm going to discuss N-coupled oscillator problem. Okay. Um, in the last lecture, we discussed how we can tackle the problem of a system of a few coupled oscillators. All right. Particularly for 2, 3, or 4, or 5. All right. What we need to do is to apply the normal mode approach to get a determinant of the coefficient matrix. And in order to obtain the desired normal mode solutions, we need to solve a set of algebraic equations, homogeneous algebraic equations. All right. And requiring the determinant of the coefficient matrix, we need to find all the desired roots for the so-called normal mode frequencies. As we have more and more oscillators, coupled oscillators, and then we need to solve a set of n coupled homogeneous algebraic equations, right? It turns out that finding roots of a polynomial may not be easy. Of course, we can do it numerically. As long as we have a fast enough computer, that will be fine. We just dump it to the computer and let the computer do the dirty work, and we just wait for the results. However, if n gets larger and larger, then the computing time will be longer and longer, right? However, for some particular case of n-coupled oscillators, where n is very large, we may be able to obtain solutions in closed form or without the help of a computer. All right. Here today, we are looking at a particular system. As shown in the figure, we have a set of n masses which are connected by identical springs of spring constant k, and the equilibrium between any two masses is A is equal to A. And all these identical masses have the mass m, and their displacements are labeled as eta I for the ith mass. All right. So for the displacement of the first mass is eta 1. The displacement of the second mass is eta 2. The displacement of the nth mass is eta n. All right. So this is the basic setup of our problem. So to begin with, we construct, we've tried to calculate the kinetic energy term first, and then the potential energy. Okay. The kinetic energy is very simple because all the masses are the same. So the total kinetic energy is 1/2 m times the sum of all the velocity square. Okay, velocity square, all the velocities of each particle. The velocity of each particle are summed together to give this term. For the potential energy, what we need to do is to sum up all the potential energy associated with each spring. Now we have to remember that eta naught, this one is equal to 0. Why? This is a fixed n. Eta n plus 1 is also equal to 0 because it is a fixed n as well. All right. So the potential energy is sum over all these relative displacement square. As a result, the potential energy has n+1 terms. On the other hand, the kinetic energy has only n terms. Now, once the kinetic energy and potential energies are available, we can construct the Lagrangian as T minus V. All right. Once we know the Lagrangian, we can write down the Euler-Lagrange equations. So for the ith particle, we have m eta I double dot equal to k eta I+1 minus eta I minus k times eta I minus eta minus 1. Why do we have two terms? Now, remember that each eta I are connected to two neighboring points. One is the I+1 mass. The other one is I-1 mass. All right, so there are two terms altogether. So let's follow the standard procedures of the normal mole approach. Assume the normal mole solution as in equation 4, all subsystems of the system oscillate at the same frequency. Okay, so eta I equal to capital Xi e to the power I omega t. Remember that this I is purely imaginary unit, and this I is the label, is the index of the particle, of each particle. Now, substituting the normal mole solution to the Euler-Lagrange equations, are the set of coupled second-order differential equations will be reduced to a set of homogeneous algebraic equations, as shown in equation 5. Here, I have introduced a lambda parameter here to simplify the notations. Lambda is equal to 2 minus omega squared divided by k. Now, in order to have a non-trivial solution, then we have to require the determinant of the coefficient matrix, as shown here, equal to 0. Now, this Dn is a polynomial of degree n in lambda, and hence possesses n roots. Then we apply the Laplace expansion approach along the first column here to find the value of Dn, okay, the determinant Dn. Now, apply the Laplace expansion, we have two terms. The first one, okay, lambda times the determinant Dn minus 1, okay, and then pick this term. There is a minus 1 times minus 1 to the power 1 plus 2, all right, the standard Laplace expansion. And then we have the Dn minus 2, okay? Now, this recursion relation is very useful because you can see that once we know the D1, D2, then we can determine D3. Once we know D2, D3, we can determine D4, so and so forth, up to Dn, all right? Now, the standard approach of normal moles approach is that we have the once we find the Dn, which is a polynomial of degree n in lambda, then we have to find the n roots. If n is huge, then this root finding procedure may not be so easy, all right? So we will try to attempt an alternative route. Of course, you can argue that who cares? We have computers, we have very fast computers, supercomputers, so we can still follow the standard procedures, find the n roots. Once we find the n roots, we can find the n special solutions. Once we find the n special solutions, then we can find the general solutions. All right, so that is fine. That is fine. However, here today I'm going to tell you how to obtain the n solutions in a simpler way for this particular case. So we, by looking at this recursion relations, it looks like uh, uh, a second order derivative. Uh, put it this way, it looks like the finite difference approximation of a second derivative. Okay, so if the second derivative is equal to 0, then it's natural for us to assume that it takes the form of an exponential function. So here we assume that it takes this form, an exponential function of n. All right. Keep in mind that a and b are arbitrary constants to be determined. So we substitute this dn into this expression in equation 7. Then we get very nice results. We have e to the power ib plus e to the power minus ib equal to lambda. All right, that means combine this term and this term. We have equal to lambda. Okay. Now, taking a closer look of these two terms, we recognize that it is equal to 2 cosine b. So we have 2 cosine b equal lambda. Apparently, b has two positive roots, two possible roots, or two possible values. Namely, b can be plus or minus arc cosine lambda divided by 2. All right, and these two values we denote these two possible values as plus or minus psi. All right. Now keep in mind that the solution, these solutions are possible only if the absolute value of lambda is less than 2. Why? Because the absolute value of cosine of a cosine function is equal to 1. So lambda cannot be larger than 2. Right? So the general solution of equation 7 is given by this. So dn is equal to a plus e to the power in psi plus a minus e to the power minus in psi. All right. Where the constants a plus and a minus can be determined as follows. d1 when n is reduced to 1, then we have lambda only. All right, 1 by 1. So d1 equal to lambda equal to 2 cosine psi. All right. d2, if we look at the two-dimensional case, this one, two-dimensional case. All right, lambda minus 1 lambda, then we have a lambda square minus 1. All right, lambda square minus 1. So it is equal to 4 cosine square psi minus 1. All right. So we have two equations, two unknowns. So we can, by Cramer's rule, we obtain a plus equal to e to the power I psi divided by I2 sine psi. A minus is equal to the complex conjugate of a plus. As a result, we can express dn in closed form as this. Okay, so very nice. We can obtain the dn in a very nice form. So we want to find the nth roots of dn. Obviously, in order to have dn equal to 0, then we have this sine n plus 1 psi divided by sine psi equal to 0. Okay, which has the following distinct solutions. N plus 1 times psi n equal to n pi. N is equal to 1, 2, 3 up to capital N. So we obtain the n solutions already. Once we obtain the n solutions, we can determine the n frequencies. All right, n frequencies. The n frequencies the eigenmode frequencies, the n eigenmode frequencies are represented by or expressed by this nice formula. Okay. So now we have to double check whether the absolute value of lambda is less than 2. Since omega squared divided by k less than 4, all right, we evidently have absolute value of lambda less than 2 for all n roots. Okay, so our assumption here is correct. Okay, our assumption here is correct, and it is exactly what we have, and the solutions are the desired solutions. Okay, so in this very nice example, we can see that we don't have to perform root finding for a polynomial of degree n. Okay, when n is very large. Okay, but of course this approach is not always applicable. It is applicable to this particular case, in which all the masses are the same, all the spring constants are the same, all the equilibrium distance are the same, right? So we have this kind of a symmetry, so we can get a very nice results for the determinant, n by n determinant, and we can obtain the n eigenmode solutions very easily. In fact, we can express the n by n determinant in closed form in such a way that all the eigenmode frequencies can be obtained in closed form. All right. Okay. So that's all I want to tell you about the n-coupled oscillators, a very special case. As you can see that if we have A getting smaller and smaller, and n getting larger and larger in the limit of infinity, and a in the limit of 0, all right, infinitesimal, and in such a way that we have a so-called uniform average density along the whole system, the whole length of the system. Now, in that special limit, we actually have a string, okay? Something like a string. So this is a sort of an elastic string. We can stretch it, and then and it can contract, right? So of course, for a common string, instead of having the longitudinal oscillations, it has transverse oscillations, but the analysis is the same, all right? So instead of analyzing the longitudinal oscillations of n mass points, we examine the transverse oscillations of n mass points, and then finally taking the limit n approaching infinity, a approaching 0. However, the average mass per unit length is uniform. Okay, so if we can approach that limit, then we have a vibrating string. So that means we have a continuous system. All right. So the normal Moore approach is very powerful, and straightforward. And this normal Moore approach is very useful in analyzing signals and systems or linear circuits. All right, I think that's it for today. As you know, we have resumed face-to-face teaching, and I hope that all of you will try to attend the face-to-face teaching as much as you can, so that we have a better discussion in the class, and I can make sure that all of you understand the materials. Anyway, okay, see you in next class. Bye bye.